Okay, so resuming with our problem here. So hopefully that we stopped here. So you took the derivative and then set it equal to 0. In order to do this, so I went ahead and converted y raised to the negative 2 back to a fraction, so y squared in the denominator. Cross multiplied here, cross multiplied, and then solve for y. Took the cube root of both sides. You get y equals 4. And again, here we had to think about our restrictions on our domain. So that's why you see, again, we can't have 0 dimensions of our box or a length or width of 0. And then the most that we could have up here is that we had 32 cubic inches. So that had to be restricted. So you can see when you plug that into the derivative in this point in time, you get that to be a minimum. So now we need to find, I believe it's asking for the dimensions. Yes, find the dimensions of the box that can be built. So I'm going to go ahead and use what we did here with x equals 32 over y squared. So x equals 32 over y squared. Because we get our y value to be 4, so that'd be over 4 squared. So we get an x value of 2. So our dimensions are going to be 2 inches by, and again, remember we had y and y as the base. So we'd have 2 inches, 4 inches, and 4 inches. This would be our dimensions of the box. Okay, so let's go ahead and take a look at our next problem. A farmer has 1,600 feet of fencing to enclose 7 rectangular adjacent pig pens. What should the dimensions of each pen be in order to maximize the total area? So again, a farmer has 1,600 feet of fencing to enclose 7 rectangular adjacent pens. So let's draw that first of all. So we have rectangular adjacent pens. I did not draw that rectangle very well. Let me try that again. Okay, so 7. Better rectangle. So we're going to do, there's 1 rectangle, 2, 3, 4, 5, 6, and then we'll add 1 on here, 7. So we have a few different ways that we can actually label like the length and width of this. We could either, 1, label the entire side as W and then this side as the length, or we could measure, put each one of these as individually as W. Doesn't really matter which way you want to go. We'll just go with this way. That's the first way that I stated, but again, both of them will work. So again, it says a farmer has 1,600 feet of fencing to enclose 7 rectangular adjacent pig pens. What should the dimensions of each pen be in order to maximize the total area? So we're going to maximize the total area, but we first have to think about perimeter. So we have 1,600 feet of fencing. So the perimeter is going to be, we have 1, 2, 3, 4, all these. So we have 8 lengths, and then we have 2 widths for our 1,600 feet of fencing. So all these individual ones up and down, the vertical lines, and then the 2 horizontal lines. So 8 vertical, 2 horizontal will be our perimeter of our fencing. And then we're talking about area here. So we want to maximize the area. Well, area is length times width. So again, a little bit of algebra. I'm going to go ahead and solve this top one. I'm just picking a variable. I'll solve it for W. So 1,600 minus 8L. Divide that by 2. Now we can substitute that back in for our area here. So we'll have 800 minus 4L times L. And we'll distribute that through. And again, we're trying to maximize this, so now we take the derivative. So 800 minus 8L. And we need to find our critical numbers by setting it equal to 0 and solving. So we'll get L to equal 100. Okay. Test it on our number line. So 100, and then again, oops, we have restrictions on our domain here. And hopefully you realize we cannot, again, have negative numbers, so 0. And then it goes up to the amount of 1600. So those would be our restrictions there. So plug in any number. I would choose maybe 1, plug it into your derivative. Again, see if you get that to be increasing, decreasing, and then something above 100. Go ahead and do that. And then push play when you're ready. Alright, so hopefully you got this to be increasing or positive on the left and decreasing or negative on the right, which does show that this is a maximum. So now we can go ahead and plug in L into our equation here. So we'll get 800 minus 4 times 100. So we'll get W equal to 400. So we have, let's go ahead and read this because this is worded a little bit different with these adjacent pins. What should the dimensions of each pen? So again, this is one pen right here. Of each pen be. So we have the length of it right here, but we need just this individual portion. Well, there's 1, 2, 3, 4, 5, 6, 7 of them for the W value. So again, our dimensions are going to be 100 feet by not 400 feet, but 400 divided by 7 feet. Because again, we wanted just the dimensions of each pen. So this W needs to be divided by 7. Okay. All right, and this concludes day 1 of optimization.